Swayam Prabha. Digital India. Educated India.
Both on your commercial computations like e-commerce and also scientific computations and lot of data analytics, etc. We use floating point extensively, right? In all media applications, for example, there is a need for using floating point in a big way. So that when we use floating point, as such, I told you that this is not an infinite arithmetic space. When I look at systems, we have limitations. We can't represent beyond something. There is a range, right? If you take 2's complement arithmetic with n bits, you can only the range is minus 2 power n minus 1 to plus 2 power n minus 1 minus 1. We can't go beyond that range. So because of this finite representation, what are the problems that you will land in? If you had just looked at integer arithmetic, the problems are very simple. So if the range, if I give you n bits and the range is between minus 2 power n minus 1 to plus 2 power n minus 1 minus 1, either you will go above that range or below that range. So underflow and overflow were the two things that you saw in integer arithmetic. But when we go to floating point, the thing becomes little more complex. So let us understand that with a set of very nice examples. So these slides are made by Professor Shankar Balachandran. He is with Intel now. But so I am just borrowing that slides, some excellent slides, and we will try and understand especially what is the difference between things like what is precision, what is accuracy. Those things become very, very important when we look at floating points arithmetic. Okay. So it is a very, very crucial aspect of this course, and I hope we will learn that in the proper perspective. I will teach and you will learn in the proper perspective. So these are the references for this. So Hennessy and Patterson's book on computer organization, IEEE 754 standard, then some web pages and Wikipedia. Now let us start the lecture with what do we understand by the term accuracy, what did we understand by the term precision. Accuracy and precision are two very important engineering metrics. What is accuracy? How close is the measured value to the true value? That is what we mean by accuracy. What do you mean by precision? We keep doing an experiment repeatedly. How close are the results, right? If I experiment, so if my results are if I repeat the experiments and I get almost the same result, then I say my arithmetic is precise, right? So accuracy means how close is the measured value to the actual true value. Precision is how close do repeated experiments yield similar results, right? So this is the difference between accuracy and precision. So we need both accuracy and precision, because if I run a program say n times, every time I want the same answer. I do not want different answer, and I run a program in machine 1 and I run it in another machine 2, I need to have the same answer, correct? So that is what I mean by a precise computing environment. And the answer that this computer generates, or whichever computer generates, how close it is to the actual value, that is called accuracy, right? Are you able to distinguish between these two? Now, so there are four combinations of results possible. I will have an accurate result and a precise result. I will have an accurate result but imprecise result. I could have an inaccurate result but precise, inaccurate and imprecise. Okay. So all four combinations are possible. Now, how? We will now see some experiments, right? I will put those experiments here. You can go and check it out. Very, very simple programs. Now you can check it out on your real system. You can write those C programs and compile and execute and see for yourself how each of these four combinations are possible in floating point arithmetic and what sort of care we need to take, right? Are you getting this? Okay. There is a difference between an precise, accurate fellow and a precise fellow. Let us be shooting dots on that target, right? Now, what you see on the left hand side, it is an accurate hit almost accurate hit on all grounds, like we were very close to that whatever that middle red circle, but it is imprecise. Different times I hit the dots are far off from each other. But on the other hand, when you see on the right hand side, it is inaccurate. We never the dots never reach the center circle, but precise. Okay, right. So this you should have it in mind. I'll give several analogies like that as we proceed. So where you should understand what is accuracy and what is precision. Okay, and especially when you start doing these are some things which. Okay, now let us look at floating point representation, right. So before going to that, what can we do with n bits if it is unsigned? So if it is unsigned, so I can represent anything from 0 to 2 power n minus 1. If it is 2's complement, it is minus 2 power n minus 1 to 2 power n minus 1 minus 1. Just 1's complement I can do minus 2 power n minus 1 plus 1 to 2 power n minus 1 minus 1. So these things we have seen in your digital course and of course in your CS 100. But when you want to represent large numbers, say for example very big one or very small numbers or rationals, irrationals, transcendentals like pi e, right, then we need a different representation, and that is why, and that representation is very crucial because there needs to be some standard. We can come out with infinite ways of trying to represent these numbers, so there was a need for getting a standard, and that is why the IEEE 754 standard came into place and we started off from that. Okay. Now what we will now discuss is about the IEEE 754 standard. Now this is overall the IEEE 754 standard. So I want to, what is this number 6.02 into 10 power 23, remember, right? This is Avogadro number. Okay. So what we need here, we need a sign, a magnitude, then a mantissa, a decimal point, then exponent, and then a radix and a base for a exponent, right. So I need so I have an exponent, I have a whatever fraction there, and then I need a sign bit. So for example this 6.023 into 10 power 23 can be written as 0.6023 into 10 power 24 with a plus sign, right. Similarly your 1.673 into 10 power minus 24 can be written as 0.1673 to the power minus 23 and a sign here plus 1. Okay. So there is an exponent, there is a mantissa or whatever the fraction, and then a sign bit. Okay. This is the basic representation here, but we want to make this look. So I could have, see why I say there are infinite ways of representing this. I can represent it as 0.6023 into 10 power 24, or I could have even represent it as 6.023 into 10 power 23, or I could put 23 here, I could put 60.23 and put 22 here and so on, right. Or I could put 0.062023 into 10 power 25, right. So I have different ways of representing this. Okay, so I need to have some standard. If two computers start representing in two different ways, what will happen is your program can never be portable across systems. So if I write a program for say some Intel machine, then I can't use it in say IBM machine. If I run for IBM machine, I can't use it in Sun Spark machine or DEC machine, right. So I need to have a common floating point representation so that I could use it, I can port my programs. So you sell e-commerce programs, you sell e-commerce software, you sell engineering computation softwares like MATLAB, etc., right. So we can't write different software for different architectures, right. We need to write one architecture and compile it for different machines. So that's why this standard has come up, right. Now this is the IEEE 754 floating point format, where there is one sign bit. This is a single precision. When you say float x, right, this is what you see there. It's a 4-byte representation. So 23 bits 0 to 22, 23 bits are used for m, that is the mantissa, and there are 23, 8 bits are used for the exponent and 1 bit is used for the sign. Okay, so it's fine, right. If s is actually 0, then it is positive. S is minus 1, then it is negative. So sign bit is very clear. If I put 0 there, it's a positive number, 1 is a negative number. Now how do we store the exponent? We store the exponent in what we call as the 127 XS 127 format. Whatever is the exponent you want, you add 127 to it and store it, right. So by that, the exponent is always a positive number when it is stored here. So if I have minus 1, suppose I want to store say 10 power minus 127, you add 127 to it and store 0 here. So your exponent value will go from 0 to 2 power 8 to 8 bits na 255, 0 to 255. Essentially you are storing from minus 127 to plus 127, right, plus 128. So every time you add 127 to it and store it, right. So always your exponent is going to be a positive number. Exponent that is being stored here is a positive number. Though you can store actual representation, you can have negative exponents, but since you add 127, it becomes a positive number. And then how do you get the fraction? This is ones and zeros. So you make the fraction as 1.1101 or whatever. You don't store that 1. You store whatever is after that decimal point. Okay. So what would be the value of this? So suppose I am storing s, e and m. The value of this is minus 1 power s, right. So if s is 0, then it is 1. If s is plus, then f is 1, it is minus, into 2 into e minus 127, because you have stored it in XS 127 format, into whatever m here, 1 point m, right. So whenever I get a binary, so if I get 0.00111, I will store it into say some 2 power 15. I will now make it as 0.110, let me put, I will make it as 1.011, I am 3, right, into 2 power 12, right. You got this? And I will store 0.011 here. I will store I will store 011 here, and of course 12 plus 127, I will store 139 here, and of course I will store 0 here. 011 is some 3 whatever, okay. So 139 I will store it in binary, I will not convert it here. So when I want to retrieve it, it is going to be minus 1 power 0 into 2 power 139 minus 127 12 into this 1 comes here, 1 point whatever I have 0 1, which is nothing but this. Okay, you are able to appreciate this. So the good thing is that exponent is always positive and mantissa is normalized. They use the word called normalized. Normalized in the sense that this is the unnormalized value. Normalization is essentially to bring 1 here and 1 point something. So to convert your whatever number you have got into the form as 1 point something else, and that something else is stored in m, 1 is not stored. Okay. So 1 is implied here. Okay. Are you able to follow this? Yes.
How would you represent 0?
We will come to that. So m is the mantissa, which is the magnitude of the number, normalized. There is a hidden integer bit 1, and of course the actual fraction is 1 point m. So let us look at this. So S is 0, S is 0 here, E is 124 and M is 1 point whatever this whole thing. So when we convert this part, this is 0.15625 as you see here. So this whole thing. So how do you convert this? Minus 1 power 0 because into 2 power 124 minus 127 which is minus 3 into 1.01 whatever. This is 2 power minus 3 into 1 point, if it converts 0.1 from binary to decimal it is 1.25. Right. So 1.25 divided by 8 because 2 power minus 3 is 8. So this is 0.15625. Right. So this is how 0.15625 will be represented. Right. So you have a 23 bit mantissa, 8 bit exponent and a sign bit. Okay. Now again, so this is again a negative number minus 1 power 1 and E is 133. So this is 2 power 6 and this 0.1101 whatever, it's 1 point this. So this is now currently minus 1110 whatever you see here into 2 power 6, right, I just bring it here. When you convert this, this is minus 118.625. Okay. Just a positive number with a positive exponent, negative number with a negative exponent, decimal. So I am just giving you two examples, very straightforward to look at. Okay. So single precision I can represent numbers like this, right, but when I want something like this, right, so when I want something as big as this, right, a single precision I can represent numbers like this, but if I want to have bigger numbers, right, as you see here, then we go in for a double precision. So how does the double precision work? It is 64 bits, that is 8 bytes, same funda, no change here, but except that this is 11 bit exponent, 52 bit fraction and 1 sign bit. So with 11 bits what we can do? We do an excess 1023, like what we did for excess 127, we can do a excess 1023, right. So that means we would have a very big range here. Okay. So interestingly, this is the minimum number and maximum number that could be represented, right. Not just minimum and plus or minus 1.175 into 10 power minus 38 to plus or minus 3.4 into 10 power 38. This is the range, right. There is a plus or minus here, there is a plus or minus here, and this is the thing. So this is binary converted to decimal for a single precision. Similarly, when you go for double precision, this is minus 308. Okay. So this is the range in which we can represent. Okay. Yeah. So please note that my range comes at most 9 times in my exponent, right. When I go from single to double, I increment it by 9 times, almost 9 times. Yeah, 8 times. Right. Almost 8 times my exponent can increase, 38 to 308 and minus 38 to minus 300. Okay. Right. So this is how floating and floating single precision and double precision are actually represented. Okay. Fair enough? Are you able to follow? Right. Now these are some special values, like you asked, how is 0 represented? Your exponent is 0, your mantissa is 0, then the value is 0. 1, how do you represent? Your exponent is this and your mantissa is 0. Okay. So these two, and there are numbers which we cannot basically normalize at all. It is so small, right. So it's called small denormalized numbers. So these are all some large denormalized, the smallest and the largest, right, where I just can put 1 here, largest is all ones. So if your exponent is 0, sort of this becomes a denormalized number. A largest normalized number is of course this, smallest normalized number is this. You can represent infinity as this, and if this is non-zero, then this is not a number, meaning I can't represent it, is out of this range. Okay. So these are some special values that we need to keep in mind, because there are some numbers which we cannot normalize, because your exponent becomes much smaller than that. So those numbers we put the exponent as 0 and put that number here. So these are all, this is the smallest denormalized number and this is the largest denormalized number. I can't express it as 1 point something into 2 power this, because it exceeds, it is outside that 0 to 255 limit in your even in your excess form, either below or above, right. And similarly, okay, so this is the largest normalized number and smallest normalized number. Then I have a representation for infinity and something which I cannot represent, even denormalized I can't do, then I call it as not a number, right. Many times when you start doing floating point computation, you will get nan. What is nan? Right. This is something that I can't represent in this representation, right. So this 1, 2, 3, 4, 5, 6, 7, 8, this is for single precision. Of course the same can be extended for double precision, but you should understand that when I interpret a floating point value, if I interpret those 4 bytes, that interpretation is not very straightforward. There are of course if you have a non-zero exponent and a non-zero significant, it's not just if I accept these 1, 2, 3, 4, 5, 6 combinations that you are seeing here. Other than that, that interpretation is what I have told in the previous slide, but these 6 combinations you should be very clear. Okay. So this is extremely important. These are some steps we need to keep in mind when we start looking at floating point representation. So now with representation itself we had these type of issues. When we start computing using floating point, then we need to be much more careful. Now let us take this, right. We need to be very careful in the sense what sort of accuracy and precision and range I need, right. I need a bigger range or a small range. So what sort of accuracy and precision I need there. So I have to go and pick, one of the decision I need to take is whether should I have a single precision or a double precision, and that is also very crucial, right. And when I scan and print floating point values, what is actually there in the memory will not come out, because your printf and scanf also does some jugglery with your floating point when it is printing it. That also you should be aware, right. Printf, when it wants to print your thing, it does some rounding, it does some truncation, okay. Even your scanning, so your scanf and printf in your C. We should be bothered about the ranges and accuracy and precision, and based on that we should select what we want to do, and the results that you get, right, the results you get, you can't just rely on printf and scanf for the results, right. Your computation can be accurate, but the way it prints it can be different, okay. So we will see some very interesting examples. So we will see all these gochas, okay. So first one thing, if I have 32 bits, I can represent 2 power 32 values. So how many floating point numbers are really there? Uncountable, right. This is the Cantor's argument, right. If you have studied that, it's fine. If you have not, it's uncountable, because between 0 and 1, between 0 and 0.1, between 0 and 0.01, then I can keep on, right. I could have infinite number of floating point values. A real line, real number line is really a continuous line. Integer line is a discrete line in sense. So, but our representation is finite in size. So I have been repeating this, I will repeat it, because I believe 7 times if I repeat once it will get into your mind, okay. So now please note that the problem is here, that I have infinite numbers, infinite floating point numbers, but I have only finite size to represent it, and because of that what are the things that are going to happen. Let us see some examples. What do you expect here? I start with a equal to 1, it's a long, I is a long number, that's okay, fine, int, this is a single precision, for I repeat it 100 times, and every time I am going to subtract 0.01 from this. So what is the answer? You should get 0, right? Note that your expected output is 0, but actually a printed output will be 0.00001. But the actual value that will be stored in your memory is some 6.591 into 10 power minus 7, right? So you can, how do you see? You take this A, okay? So this you can just print, this mathematically you calculate, this is what you print, you will get it. If you use GCC, you will get something very close to this. But how will you find this? Multiplier. No. What you do is you cast A as a character pointer, right? And print those 4 bytes of A, and actually find out what characters are there, that ASCII character, ASCII values, right? Right, you can cast it as character and print that 4 characters starting from that point, right? You can give a pointer and increment the pointer and print the contents, and from there you calculate exactly what it is. You will find out that this is the value that is stored in the system. So first thing is, mathematically it is incorrect, and what the computer actually computes, this printf doesn't print that, it is printing something else also. So the printf itself has something to go and massage it and give you some answer, right? So what you see as a printout as an answer is not actually what is stored in the memory, and it is not the actual, mathematically what is stored in the memory is not the correct answer, right? You see, there are 2 levels of inconsistencies that creep in. Imagine that I take this answer, I put it into a file, and some other time later somebody takes this answer and do further floating point computation. Already you have got an erroneous result, and that error still creeps up and becomes a bigger error, correct? So this is something, I don't know, did you learn this in your CS 100? Was this taught? Yes? Oh, good. Okay, so a lot of redundancy, but still I will continue. Okay, now so the error actually crept in while we were subtracting, right? So why? Because some of the intermediate values were not able to be represented faithfully, right, exactly, and then the error propagates. But why the print statement printed it as 0.00001? Because the printing actually rounds it off. So it says, as you see here, you see 1, 2, 3, 4, 5, 6, 7. So this 0.06 actually became 1. So printf actually rounds the value. So these are, yeah.
So what do you mean by the intermediate values?
Like 0.01, right? 1 minus 0.01 is 0.99, 0.98, right? When I want to represent 0.99, it will not be exactly 0.99 because of your finite arithmetic.
But in our example, 0.99 can be like faithfully represented.
Faithfully it can't be. It will be some 0.999 something.
The rest is 0, right?
No, it's in binary, right? Oh, yeah. So I don't have a decimal arithmetic. Okay, binary it will, yeah. Just try it out. Now let us see what will happen here. So I am subtracting from a equal to 1, and I am subtracting it 100 times and adding 1. So the answer should be again 1. So the expected output is 1. Now you want to say 1, we will say 1 plus delta. Okay, so actually the printed output is 1, because you expected 1 plus delta, but actually it comes 1, it becomes accurate, and the actual value stored is also 1. Okay, so 2 negatives make a positive, so the error in subtraction got compensated by the error in addition. Okay, So sometimes errors hide each other, so they complement each other. Okay. Error creeps in during addition now as it was in subtraction. Error propagates as before, but one error cancels the other. But why printed as 1? Because now it is printing it faithfully. Okay. Right. So please understand, these are all the issues that we land up when we start doing these type of floating point computations. So I will give you a simple exercise. Let us repeat this previous experiment with subtractions of 10. We did it with 10 power minus 2, right, minus 0.01. Do it 1000 times with 10 power minus 3, 10 power minus 4, 10,000 times, and 100,000 times with this. And correspondingly have the loop should be 10 power 3, 10 power 4 and 10 power 5. But actually you will see that the actual value that will be there, would be in the system. What will be printed is this for the first experiment, that is just subtraction. Subtraction plus addition is always the error gets cancelled. Okay. Right. So please see that smaller the value that is subtracted, more the error. Right. That is also very important. So when so this is becoming 10 power minus 3. The error was 10 power minus 6 here. It became 10 power minus 3 here. Error was 0.00009, which is now become 0.09478. So some orders of magnitude the error has crept in. So smaller that I am going to subtract, 1 minus 0.00001, then smaller the thing I subtract, more the error. Right? Are you able to see this? And that error is growing exponentially. So here it was in the 7th place, 1, 2, 3, 4, 6th place, let us say 10 power minus 6, here it became 10 power minus 5, here it became 10 power minus 4, 10 power minus 3, every time it is getting multiplied by 10. So the error also basically grows exponentially. And the values are faithfully restored in every single case, because that means what? When I subtract and then I add, then it is basically faithfully represented. So that means the error is systematic, right. So there is something happening wrong in that subtraction, exactly the opposite thing happens in the addition to compensate for it. So does it mean this error is predictable? So this is some question that we need to answer. Okay. But just note here that error, if I go and become more and more accurate, right, I want to become more and more accurate by increasing my floating point value. If I want to keep decrementing by say 10 power minus 5, minus 6, minus 7, then the amount of error that accumulates becomes exponential. It increases exponentially. That is something that we need to keep in mind when we do this, in spite of all your IEEE 754 standards, everything. Right? This is something that we need to very much keep in mind. But what will happen if I do with 10 power minus 8? We have done till 10 power minus 7. Interestingly, you will find that the printed value is 1 after subtraction and 1 after addition also. The very first subtraction and addition has no effect on A, right, if I go with 10 power minus 8. So you can try the experiments with A starting at 0, subtract and bring, and you will get lot more surprises here. Okay, right? Are you able to follow? This is very interesting. So let us go and one more minute. Let us go and redo this with the double. Then actually we will see. Actually you will see that the actual value is very, very less, very close to 0, right. It is some 10 power minus 16, right, where in the previous case it was 10 power minus 5 or 6. Still the answer is erroneous, but the error is far lesser. Can still be problematic if the error is accumulated 10 power 16 times, then it actually becomes 1. Okay. So, and when we print, we also used percentage D here. If you carefully see here, we have used percentage G, which is a double printing. So it actually prints a wider range. okay, right, in contrast to percentage f, right. So, this is what we see when as 10 power minus 3 in double, and note that here also my error was minus 16 when I started with 10 power minus 3, but if I start decrementing 1 with 10 power minus 8, I am getting an error which is 10 power minus 9, but again here the error, as I keep decrementing, as I become more and more accurate in my computation, my error actually increases exponentially. This is 10 power minus 16, this is 100 times that, this is again 100 times that, this is again, and then it becomes 100 times and then 10 times. So, it starts, you see some exponential growth here, okay. So, the last one, so we will do a new set of experiments, like we start with 0 and do this. What must I be at the end of this loop? Expected output is 100, right. We start with 1 while b is greater than 0.0, do b equal to b minus 0.01 I plus plus. So, the value of I should be 100, but the value of I you get would be 101, right, because 101 times I need to subtract to actually make it less than 0. If you repeat this with 10 power minus 3, 10 power minus 4, you will actually find that this 1001, 10,000 and so on. This is not going to be 1 million, it is less than a million here, sorry, less than a lakh here. Very quickly it becomes 0. This is less than a million here, 10 million. 10 power minus 8, what would be? It will be an infinite loop, right, with single precision. Using double precision, now I get much closer to this, right. So, because of floating point, we had all these disasters because of these type of computations. The Patriot missile actually became unpatriotic, it failed at 1991. There was, the time measured was in units of tenth of a second, and it went and chopped off at 24 bits. So, for us the error was 0.34 seconds, the Scud travels at 1.6 kilometers, so it travelled more than half a kilometer away. So, I want to go and hit something here, it went and hit something later. And Ariane rocket 5 actually launched by ESA in this European Space Association 1996 exploded 40 seconds after liftoff, because a 64-bit float assigned to integer and the integer saturated. Okay, this was a $500 million damage. So, that is why we call these type of errors as a $1 million error. Okay. So, floating point calculations are tricky, you can need to do extensive checks. IEEE 754 also has inherent problems, as we have seen this. So, you have to write your own libraries. When you do floating point, you should be extremely careful in these experimentations. Okay. Thank you very much.